Right, so let's continue with the second talk of the morning, on the last talk of the day. So Phil Larsen from the University of Michigan is going to tell us about logarithmic corrections in macro entropy.
Thank you, and thanks so much to the organizers for the invitation. It's exciting to be in South Africa for the first time. I also thank them for asking me to speak the day after the banquet. So I have a story that unfortunately many people, several people in the audience have heard. That's the problem with having many good friends here. But anyway, I will tell it also at a stage that is mostly frankly for the people who have not heard the story before. So that's anyway. So let me give some introduction. As you can see, most people that do precision studies think what Gabriel was talking about, with black hole entropy. What they do is that they immediately go to discuss BPS black holes. Why do they do that? Because the conventional wisdom is that if you did not look at BPS black holes, it would just not be possible to find any kind of precision results. So you really just shouldn't even bother. Well, in this talk, I want to present some results about just explicitly computing corrections for non-BPS black holes, for black holes that are kind of standard black holes, that are the kind of black holes that we see in general relativity and that have no supersymmetry at all. And what you would expect when you compute such corrections is that conventional wisdom should be correct, you should get complicated answers, and indeed, that's what we find. In general, the answers will be complicated. But the point is going to be that the answers are going to greatly simplify in some particular environments. So this is actual environmental research from the United States. So what do I mean by environmental dependence? Well, black holes, they are often solutions to many different theories. So what I have in mind is the kind of black holes that we study in a GR type class. Let's look at just Einstein-Gravity plus some Maxwell fields. This is the Einstein-Maxwell Theory. The solutions are very well known. They're the Kerr Newman black holes. But what I have in mind is to point out just a very obvious thing, which is that the solutions to this theory are also solutions to some other theories. For example, I might wish to add some field here that appear only quadratically. The simplest field I could have in mind would be to just add a simple fermion here. That appears quadratically, is now a different theory, but I can still find a solution to this new theory. The new solution, I simply amount to take this new field and put it equal to 0. It's very trivial, but technically it's a new solution. Of course we take it. It's the same solution. It is, but it's a solution to a new theory. This is what I mean by environmental dependence. And the point is that once we look at quantum correction, it matters exactly which theory is this thing a solution to. Because these extra fields that we might or might not wish to add, they could run in quantum loops. So they will in fact change some of the quantum corrections. So we should be very careful about not what solution we're looking at exclusively, but also it is a solution to exactly which theory. And which are the theories that turn out to be interesting? They're the ones that have supersymmetry. So I will consider Kerr Newman black holes, and I will consider them in an environment that has at least 2 supersymmetries. And that's when we will see some simplifications that are quite dramatic. So what do we do? Well, first we need to embed our Kerr Newman black holes into these solutions with, into these theories with more supersymmetry. So that's it, as in considering well-known solutions in a new environment. Then we want to compute quantum correction to those. It's just explicit computation, fairly standard really. And that's where we find some simplifications, and I will do a discussion based on some sort of relatively new work on these simplifications come from what, and I will formulate that as a normalization theorem. And this is work done with Stephen Anthony and Daniel Larsen postdoc.
And will it depend on the amount of supersymmetry you already need?
No.
So
Sure,
let's say n equals 8 or n equals 4 or n equals 2 is irrelevant.
Yeah, I mean, I'll do them all, but no extra simplifications happen if you do more. N equal 2 is what matters. So the starting point, as I've already indicated, is just this standard theory. And I just want to emphasize, just because this really is sort of what the GR people often give string theorists a hard time on, is why don't we just consider standard kind of black holes? Well, I do. And I'll go out of my way to emphasize that the standard solutions to this kind of theory includes the Schwarzschild and Kerr and Weiss-Nordstrom and whatever that is just really truly standard. The special thing is that I try to make not just the GR people happy, I also would like to make the string theory people happy and saying that, oh, but I also want to limit where this thing here really truly does become supersymmetric, where not only the theory is supersymmetric, but even the black hole itself preserves the supersymmetry so that we have a BPS black hole. So there's a limit for that too, basically, when there's no rotation, when the mass is equal to charge. We can add fermions and make this into a supersymmetric black hole. So that's not the limit that I'm particularly interested in, but I am interested in the fact that I'm doing something that can be continuously related to the supersymmetric limit. I can deform it, and I can deform it then very far away. So we want to take these solutions here, standard solutions, and consider them as a solution to n equal to supergravity. How do I do that? Well, first thing is that I just start out with saying, look, let me consider minimum n equal to supergravity. That's really easy, because the bosonic part is identical to the Einstein-Maxwell field. There's gravity, and there's a graviphoton, and the actual bosonic action is precisely the Einstein-Maxwell. All I need to do is to add two gravitini. Well, those are just equal to 0. So therefore, I'm done. I already considered my Einstein-Maxwell theory, my Einstein-Maxwell solution as a solution now to n equal to minimal supergravity. That was too simple. That was super boring and trivial. So let's try to do a bit more. Let's try to do n equal to supergravity with some extra vector multiplets. Then it gets more complicated. We have gravity. We now have a bunch of vector multiplets sitting in here. We don't have just our graviphoton, the field strength. Instead, we have here sort of NV plus 1 field strengths. There's the 1 that was part of the gravity multiplet, and the NV that are some extra ones that I'm now adding by hand. These extra ones are equal to partners, so they also have scalar fields. And everything is put together in this way that special geometry is telling us that we must. There's a coupling constant function here in front. It depends on what the scalar fields actually are. There's some coupling constants in front here, basically because of the calorimetric. And all of this is packaged together in this way that special geometry tells us that we must package things in. So that's an equation that's a bit complicated, and we can say, good, could I perhaps consider my Kerr Newman black hole as a solution to this theory? That now has a bunch more vector multiplets. Well, I would like to think about this as being, in my philosophy, that I really don't want to change the solution too much. I don't want to change the geometry. I want to say that it's the same solution. It's just finding itself in a new environment. So in order to change the solution in the minimal way, I have to specify all these new fields, like my field strength and my scalars. And the best I can do is to say, let me take all these scalar fields to be constant. This is the most boring thing to do, is because that way they don't add any extra energy and stuff like that. So of course I have to specify what the fields are, but I just take them to be constant. This is the closest I can do to kind of the way I did for the fermions, was to just take them equal to 0. It's the same solution, quote unquote. However, for the scalars it's a little bit more complicated, because it might not be consistent to take these scalars in and just put them equal to constant. The reason that it might not be consistent is that there were these coupling constant functions here in front of the field strengths. So in general, if I find my equation of motion for the scalars, this will give some kind of Klein-Gordon type equation. And then this thing here, once I vary with respect to the scalar fields, will give some kind of source term in my Klein-Gordon equation. And in general, that source term will be non-vanishing, and therefore it wasn't even consistent to take constant scalars, because once I add with a Klein-Gordon operator, that will give 0, and then my source term will ensure that actually the equation of motion is not satisfied. Well, we look and analyze a bit that source term, and it turns out that there is a nice solution where the source term vanishes. The parameter that I can use for this game is that I have one field strength in my Einstein-Maxwell theory, of course, the Einstein-Maxwell field, but in this bigger theory I have NV plus 1 different field strengths. What I should do is that I should specify which of the NV plus 1 field strengths is it that I should identify with the Einstein-Maxwell field. Well, this is the one that is the full NV plus 1 different field strengths, and what I'm saying is that once you have told me what the scalars are, you see that xi, this is how you should identify the full field strength in the n equal 2 theory with my field strength from my Einstein-Maxwell theory. And clearly it's the only thing I could have done that was kind of consistent with duality symmetry and things like that. It's certainly the simplest thing I can think of. And if you put this ansatz in here, you will check that the source term that a priori did not vanish, in fact does vanish due to special geometry identities. And that way we can say, good, if we identify our Einstein-Maxwell field with precisely this linear combination of my NV plus 1 n equal 2 fields, I have an actual solution to my n equal 2 theory. So I've embedded my solution from Einstein-Maxwell theory into my bigger theory. My interpretation of this is something that might have special interest here also, is that I think about this as being a version of the attractor mechanism. I have no supersymmetry at all. As you know, in the attractor mechanism, what you do is that you usually have in mind that you have a bunch of charges, and the charge is kind of equal to the mass, quote unquote, doing some supersymmetry BPS relation. But the charges will act as sources to your scalar field. So your scalar field is whatever it is, wants to be at infinity, you just specify it, and then as you flow in, the forces due to these charges will force the field to go into a special value near the horizon, and that value is the attractor value. Very standard story. It also relies very much on these charges, it relies very much on the supersymmetry. This is the story that's pretty much the same story, but stated in the opposite direction. Let me not specify charges. I specify the scalars. And then after that I say, good, given these scalars, these sort of attractor scalars, what charges would it take to make these have the right value? These charges is what it would take. So in the extreme limit, where this is supersymmetric, this would be kind of like running the standard supersymmetric attractor mechanism the opposite way. Instead of using these are specified charges, tell me what scalars I must have at the horizon for those charges, do it oppositely. Specify the scalars and tell me which charges would be legal for that. So that would be the BPS version of this kind of attractor mechanism. But now you can then say, good, let me actually generalize that. Where I don't really just talk about charges, I talk about fields. And that way I extrapolate everything away. And this statement now is a statement that's written in a way where your standard BPS attractor, in fact, is valid even in this totally non-supersymmetric situation. So it's running the statement backwards, and now it's one that generalizes nicely to the totally non-supersymmetric situation. Kevin, you said that, I think you said that this statement was in your paper. I looked. Show me.
It's not exactly. I mean, it's equivalent that, so for scalars to be constant, you can express the same statement in terms of a black hole potential.
Yeah.
And the black hole potential has a minimum, whether you minimize it with respect to, you know, if you, yeah.
No, I think your minimization condition is got to be equivalent to this, but
yeah, it's not exactly, it's not the
but
same
you will
thing.
forgive me for not having noticed that.
No, it's not the same thing.
You know, so the most general setting I'm going to have is that I'm going to consider any theory that they equal 2 supersymmetry or above. In those contexts, it's convenient to summarize my matter as saying that I have just, I'm going to express everything in terms of n equal 2 fields. So what I have is necessarily one supergravity multiplet. Then I have a bunch of extra gravitini, because my baseline is going to be n equal 2, but when I want to go above n equal 2 supergravity, I need some extra gravitini. Those I'm going to think about as extra n equal 2 multiplets. A bunch of vectors, a bunch of hypers, and although I only showed you just a little piece of the story, but I showed you the most important part, what we have is that we have a solution to this general theory. This decomposition is really useful both for BPS and non-BPS black holes, and our embedding takes sort of the totally standard geometry of a Kerr Newman type black hole. It's exactly the same geometry, specifies all the matter multiplets in this much bigger context in such a way that our theory, our solution, still is a solution to this bigger context. So I have a question to this point. So that's the environment and the embedding. Standard solution, but to a theory that's less standard. More standard for some other people, but anyway. All right, now we move on to quantum corrections. Gabriel was already introducing it a bit, but then introduce it a little bit more broadly. So the entropy of the black hole, of course, very famously has the area law as the leading term for the black hole entropy. Less famously, but by now fairly well known, There is a correction here. The next one is a log. Then after that, of course, you have all the dots. See Gabriel's talk. I would be interested just in the log. So let me specify exactly what I do mean by the log. We often get questions here that this is log of the area. In fact, I haven't even bothered getting my dimensions right here. So this is something that could give some confusion. The way you should think about it is that you take all length scales in your theory that have dimension length, and you think about them as very large, because it's a very large black hole. And when the black hole is very large and all length scales are big, this surely is a big number. But as I rescale all my charges and rescale them in the same way, uniformly, all length scales should be rescaled at the same time, then this log here, of course, will go as log of that extra scaling that I'm doing. So this is log, this is a large log, this log of a big scale, because I'm making all my length scales big. So the way I think about this as being just the long length scale. What I do not think about is that that area might be an actual complicated function of all the various parameters in the black hole, but that's not how you should think about it. You should just think about it as something that has that scaling. Because if I were to change this function to a different functional dependence, that would actually be something that would correspond to something that is just of order 1. So anything of that same log dependence would do. The data, in fact, comes here. The data comes from here. We have a dimensionless function. It'll be a function of the ratios of all parameters that the black hole might have, so all dimensional parameters. If you think about everything as being length scales, the ratios of these length scales would appear here. So in the same way that sometimes people, they go and they find black hole solutions, they work hard, then they compute the area. And what have you learned about thermodynamics? Well, you've computed hard by solving some nonlinear differential equations called the Einstein equations. You computed a single function of dimensionless variables, because I knew already in advance that this thing here was something of order mass squared when it comes just to how would it be dimensionally speaking. So I can think about this as being a function that I already knew from the beginning is dimensions. It was like the mass squared, but then times some function of all the dimensionless ratios. That's what I really get out of solving my Einstein equations and try to use my solution to do thermodynamics. And the reason I emphasize that parameter count is that here in principle I have as much information. Again, I have one function of all the dimensionless ratios. So since people often work very, very hard on trying to understand this term here clearly is sort of an unmined, an underdeveloped piece of data that we can extract, and that's worth computing in many different examples and trying to get an intuition for. And the reason that this one here is special is that it's something that, like the leading term, you can compute just in the low energy theory. All we need to know is what are our massless fields. We do not need to know what the massive fields are. The massive fields I can think about as just integrating out. Once I integrate them out, I can think about them as giving some local operators. And those local operators will inevitably come in the dots. They would not give anything to the logs. The logs comes from the massless fields because it's sensitive to very long distance physics. And it's the massless fields that spread out very, very far. So from the low energy theory, I can compute my log. Of course, I could also consider that from my microscopic theory, and then once I go and compare, I will have perhaps an interesting match in some cases, some good cases. Such matches have been made. That's not my agenda here. My agenda is, let's just go and mine the low energy theory and try to see what's the structure of this particular quantity. This is a new function of the dimensionless variables. What is its structure? And what can I learn? So how does one compute such a thing? It's very standard. What we need to do is to consider our solution, but not just a solution. It's a quantum theory, so we need to take fluctuations around the solution schematically. I'm thinking about that as being some kind of a phi squared. Phi here I should not think about as just a scalar. I think about it as also all the fermions, or all the vector fields, or gravity even, or something like that. But I have some kind of quadratic fluctuation operator, so this lambda here in principle is something very complicated, acting on all my fields in my theory. And has a lot of indices and stuff like that. But in the end of the day, it's just a quadratic fluctuation operator. And this is just a Gaussian integral, and I know very well how to compute it. Even if in practice there are quite a lot of indices here. Then I have to repackage, because of course I start realizing that this thing of course is going to end up diverging. So I need to regulate it. A good way to regulate it is to analyze the spectrum of this lambda operator. All the lambda, I'm going to call all these eigenvalues little lambda, and where I can rewrite the spectrum of this lambda operator in some standardized form. This is the heat kernel. And by taking the log here and rewriting my determinant, the standard formula says that my quantum effective action is W here, so basically the log of the determinant essentially. I can get in a convenient way by integrating up this d function here, the heat kernel, over this regulation parameter S, the final parameter S. So this is all very standard notation. The one thing that I do want to emphasize is that the term I'm interested in is this d function here, which I think about as this function of S. In fact, it will turn out to be a meromorphic function of S. In general, it has poles as function of S. Those poles we're not going to be interested in. What we are going to be interested in is the S independent piece in the V. Because if this one here, you start thinking about as a constant, you can do the integral and you say, oh yeah, if this is a constant, this sure is going to be a log. And it's that log that we're interested in. Importantly, what people often compute actually is not really the heat kernel, it's this K here, which would be the heat kernel density. What you do is to get from the density to the heat kernel is that you integrate over all of space. And this will play an important role later, that I distinguish between when do I have a density and when do I have the actual full result. The thing I'm interested in here is the actual full result. I have to do my integral, and that's how I get something dimensionless. Some people they would call this the integrated trace anomaly, but I won't. So how do you go about doing this? Well, in principle, this was totally standard. As I said, what I need to do is to compute functional determinants of various fields. Well, I'm surely not the first to have thought about that, and the major industry started doing this in the 70s already. So this is the sort of thing that there are not just papers on it or review papers, there are books, many books, that would have done this. So this is something that is entirely standard. But we do have to do a little bit of work. The reason we have to do a little bit of work is that we're considering our solution in a new environment. And this new environment, we've specified exactly what theory is this solution of ours the solution to. That means that we should go and take the quadratic fluctuation determinant, or fluctuations around our solution, and we should take it in the actual environment that we're in. And that turns out to give us some non-minimal couplings that the people who wrote the books would not have considered. They would consider things that, why don't we just consider minimal couplings for various kinds of fields? It's interesting to do that for many different spins. And surely they're right. But I'm interested in the actual couplings that I got from my theory. For example, if I take a fermion and an equal to hypermultiplet, then there will be a dependence on the background. These hyperfermions, they would have a standard kinetic term. This is the term that people would have analyzed and say, good, this gives me some kind of quadratic operator here, this is a kinetic operator. Let me go analyze the spectrum of the Dirac operator, and let me try to repackage it there, and then go and find my D0. That would be in the book. What would not be in the book would be the extra piece here. The one that is specified because I'm n equal to supergravity, that I must have this kind of Pauli coupling. So this would be a non-minimal coupling that comes here with a very specific coefficient that cannot be negotiated, comes with very specific forms, and it's those extra couplings that gives me a little bit of extra work. I have to go and actually analyze some new fields, because these would be non-minimally coupled fields.
May I ask a question?
Yes.
So the shock these type of terms in his paper on logarithmic corrections.
Well,
So in a sequence of papers.
that's right. But let's organize it into two sequences of papers. One where he pursued extremal black holes.
Yes.
There, he took this into account. Then another sequence of papers where he considered non-extremal black holes like Kerr and whatever, and he did not consider those. Therefore, the second sequence of papers in no limit reduced to the first sequence. We are filling in the things in the middle, and therefore having something that will agree with his results when you go to the supersymmetric case, and agree with his results when you go to something that has absolutely no supersymmetry, neither the solution nor the environment. Right? But we interpolate between these two different situations. That was exactly sort of the point of adding these extra bells and whistles, was to let's get something where the Schwarzschild black hole really can be seen as a deformation of the UPS black hole, all the way out. Yeah? So this is one of the fermions. This is one of the simplest cases of saying I have non-minimal couplings, but of course, you should also say, good, for example, these vector multiplets, I already showed you the Lagrangian is a little bit complicated. They had these funny functions with the K-metric and the coupling constant function for the field strengths, and well, I should take my actual solution, I expand to quadratic order, and when I expand to quadratic order, I get some kind of action. And of course, we definitely get some kind of action where now my bosons, which I took this to be constant in the background, but well, they can fluctuate now on my scalar fields. And of course, I have a lot of vector fields. I have not just the vector field, the one that's my is my Einstein-Maxwell field, but I have NV plus one of them. But these extra NV1, the ones that are orthogonal to the one that I'm really turning on, could also fluctuate. And that would be these fluctuations here. And then actually the scalars in these fluctuations, they couple to each other. They couple to each other in a way that's unfamiliar. It's something that, where did you get that from? Well, I took my Lagrangian and I explained it to second order, simple as that. But it certainly gives some coupling here that you would not be surprised to learn was not something that would be in the textbooks. Because, you know, where did you get this from? I got it from minimal to supersymmetry. So this will force us to do some new computations. Here illustrating I have to do certainly something for my hypermultiplets, I have to do something for my vector multiplets. It turns out that I have to do something for all my multiplets actually. So how do I do my computations? Well, there my textbook is very useful. I take my heat kernel, or more precisely, the heat kernel density at equal points, so it depends on 1 point, x. Sometimes heat kernels can be on 2, but I will not introduce that. So it's on heat kernel density. As I already described in words, it has this dependence on my regulator, on my final parameter s, and I expand that in a neuromorphic series. That will start out with some kind of 1 over s squared, that will start out, therefore have 1 over s, but also will have, when n is equal to 2, a constant piece, and it's that constant piece that I'm interested in. The way I'm going to find ultimately my logarithm is by determining this constant piece here. That way I find the constant piece in my heat kernel k, and then I will go and integrate over all of space, and that's how I find my b. So people have solved this by anticipating that surely somebody in the future will come and ask for some very crazy fields, non-minimal couplings. Look, let me just solve it for all the cases. And that's what's in the books. They say let us take a general kinetic operator, perhaps with some linear kind of term, perhaps with some kind of mass term. This is not literally a mass term that acts on my fields. It's something that could be sort of a space-time dependent mass term. That's in fact exactly kind of like my FMUs, that they kind of appear like a fermion mass, except they depend on where we are, and they have some indices and whatnot. That's exactly what is taken into account with this kind of totally generalized kinetic operator. And that kind of generalized kinetic operator, people already once and for all said, look, let me just go and compute this heat kernel here. This is the result. The result is written in terms of the geometry of my space-time, but also in terms of exactly what was the coupling omega here. It was repackaged into a kind of generalized connection, and we found some kind of generalized curvature, and that curvature also entered. So this linear term here will get repackaged and give some dependence here. So my minimal, non-minimal couplings will enter through my p, through my omega, and they will give some new terms in my heat kernel. The standard thing that you will find in the textbook would be things that ultimately came from this, plus stuff in these ones that came exclusively from the minimal couplings. Once I do my non-minimal couplings, I get extra terms from it. I have to do some work. So for example, let me take the Lagrangian for the gravitino, their gravitino, the one that gave me 2 supergravity. Multiplet. This is the standard gravitino, the one you would find in the textbooks. This is the gravitino with extra couplings as specified by N equal 2 supergravity. Well, now I take my magic formula and I plug in and chug away, more precisely the student plugs in and chugs away. And you get some kind of result. What's the structure of the result? Well, you obviously get some stuff that just gave you the geometry. In fact, this stuff here is the stuff that you will find in the textbooks, because if I take the field strength to be 0 just by hand, obviously it will reduce to what I got normally in the review papers and the textbooks. So this stuff here will have exactly the same coefficients that would be standard, the 212 or the minus 32, whatever, I'd be able to find in some suitable format from previous work. But this stuff here, I would not be able to find, because that obviously came from this. It came from this stuff here, being repackaged into a generalized connection. That generalized connection giving me some kind of curvature, and that curvature now contributing here. Let me make sure I get the dimension analysis exactly right, because this is a point where there's often confusion. So notice the schematic form. These things here are like curvature squared. Then some of these corrections, this is down here, this is written in a form that might be hard to decipher, but it's a field strength squared and another one. In other words, this is like a field strength to the 4th power. Not the squared power, to the 4th power. Geometry squared, curvature to the field strength to the 4th power. Why is that? Well, it's because my schematic my couplings were kind of like derivative plus some kind of field strength. Now you wouldn't be surprised when you put indices in, then the commutator between two derivatives gives you basically curvature. But then you should also not be surprised that once I put these indices in here on the f's, it'll give me some terms that look kind of like an f squared. Not like an f, but like an f squared. So therefore you always get something where the curvature comes with an f squared. That's good, because my Einstein equation in fact relates geometry, curvature, to f squared. So these terms here I'm going to think about as being of the same order in my expansion. And I emphasize all this because people who consider gauge theories in curved backgrounds, they have formulae that look superficially similar, but f appears to the quadratic power. It's a different coupling, and that's because people who do gauge theory, they often say, why would you do this crazy coupling? Haven't you taken a quantum course? You take b plus a. It's a, that's how you're supposed to introduce couplings. But didn't I tell you they were non-minimal couplings?
So this f mu is in the setting where you'll have one photon and a combination of...
Yeah, well, so here I've simplified. So
it's just general.
Right. So here I really should have written indeed something that had all the x's and scalars and all my field strength or whatever, and then plug in my background solution. Since I'm only interested in quadratic order, and this already appears quadratically, I can evaluate this stuff on my background. And when I evaluate it on my background, it reduces to this thing here that is really the f mu, the one that came from. So it's precisely the right sort of linear combination that appears. Yeah.
So other than telling you what you should feed into the heat kernel calculation, does supersymmetry help you with the calculation?
No.
It tells you what you should feed in, but it doesn't make anything easier.
It most certainly does not. That's right. That's right. It's even a good student, it takes a while. Yeah.
It's maybe related to this question. Is there another way to check these coefficients?
Oh, you mean that was this quarter really correct? Could it have been something else?
The ones that you have been for.
These ones here.
The second and third one.
Oh, so you're saying, okay, good. So the fact that this was 180, whatever, could I have found that some other way?
Or the ratio.
And so on. No. But you will see. You will see. I mean, you will see that in the end.
The way this question is whether we can super simplify this.
Yeah. So that's, I will explain in a second how to do that. That's right. That's right. Right. So that will, in the end of the day, indicate that, yes. So in the end of the day, at some level, you're right. That we will get a check on this, which at the present time looks kind of quite impenetrable. So what does it look like? Well, as I've emphasized, we have some various r squared type of terms. We have some r f squared. We have some f to the 4th or whatever. But now I can go and simplify, because by the entire logic here, I'm expanding around the background. The background satisfies the Einstein equation. The Einstein equation is somehow relating the curvature r to the field strength f squared. And therefore, terms like this, I could try to rewrite my f squares in terms of the r's. Now there you get a simplification that, at least to us, was very surprising. That all these terms with the dots here, the f to the 4th, the f squared, whatever, they greatly simplify. Once I use the Einstein equation, the Duality identity, the Maxwell identity, it turns out that all these f squareds, f to the 4th terms, can be rewritten in terms of the geometry alone. The geometry alone, I will express somewhat standard in just informed field theory, and rewrite in terms of the Weyl squared invariant, the Euler term. These are just standardized linear combinations of taking not just literally Riemann squared and Ricci squared, but taking some other linear combination. And people who are studying these things will say, oh yeah, that's certainly the standard thing, and the way you should do that is that you should not tell me what is the coefficient in front of the Riemann squared and the coefficient in front of the Ricci. Take linear combinations and instead tell me what is A and C. But the magic that I'm emphasizing is all these extra terms were really there, they were complicated, and what was not so obvious perhaps was that the individual coefficients here, I know this was a little bit what Shaheen was saying, is that they seem to be exactly such that one can take this and simplify it and make it into just something that depends on the geometry. That would certainly say that these coefficients here somehow were related in a way that was very special. Yes?
So you chose some scheme because there could be B, which is independent, but this C and A, they are scheme independent. And I wonder when you calculated and with regularization, which renormalization scheme you used?
Yeah, to be obviously good, I showed it, we did minimal subtraction heat kernel. That was the scheme we actually did. But you'd ask, could there have been scheme dependence in this? And the answer is no, but you're correct. That certainly in our first pass, we just contributed. And that's sort of how I described it, but in the second pass, we made sure that there is no scheme dependence. So it's, yeah.
Suppose that we took the same matter code that work supersymmetry explicitly, so that it was to allow non-zero.
This quarter here, for example, maybe I could turn it into whatever I want. Yes, that's right.
This would still happen.
So that's right. So that's a very important question. That's right. So this simplification we got now with the field strengths, they combine in just the same order. Was supersymmetry responsible for that? And the answer to that is no. It was not responsible. It would have happened anyway. It would have happened anyway. So what is responsible for it? Why is it that the explicit dependence on the field strength can be eliminated? Well, it's because of dualities. Electromagnetic duality, if you push it in our context, and here I really should have put in multiple slides, especially if I had known what Gabriel was doing, there's a story here that the higher derivative terms, they should transform in some way on a duality. In fact, as Gabriel was totally emphasizing and spending a lot of time on, they transform rather non-trivially on the duality, these extra terms. But you can work out how they transform on the duality, just by assuming that the theory is electromagnetic duality invariant. And surely our original theory was electromagnetic duality invariant. It's just, standard Dirac duality of the Einstein-Maxwell theory. So that duality gives me some phase symmetry, and that phase symmetry tells me that it must be something that the quantum corrections are going to respect. And you can figure out how must it transform under the duality at the level of the Lagrangian. What it turns out with the special embedding we have, the solution we're having, the four derivative terms do the simplest thing they possibly could. They are duality invariant. So this is where things are very, very different from the game that Gabriel was playing. Because he felt that they were not duality invariant. It's very interesting figuring out how they were not duality invariant and bootstrap that to something else. I'm saying, well, look, I'm more lazy. We looked at a very special solution. That special solution is exactly such that this actually is duality invariant. It's exactly such that that game would not be profitable to play. But it does mean now that all I need to do is that I have to go and find what are all the possible duality invariant terms I can write. Well, we did that. For example, there's a unique duality invariant tensor. This is f plus minus a self-equal and n a self-equal part. And then if you want to find things like f to the fourth type of terms, what you should do is to contract your indices in various different ways. For example, you could contract it this way here, in this precise order. There are actually several different ways of doing this. You can contract it to Riemann simple and such things. There are actually a total of 5 different ways of contracting these different things. But then you can show that given that you wrote something that was just duality invariant, where you make sure that your f plus was always multiplied by f minus. This one gets a phase, this gets the opposite phase. So this is invariant. Because I start with only something that's invariant, in all those cases, I can actually rewrite things in terms of the geometry. So the fact that the anomaly coefficients are expressible in terms of the geometry alone is because of duality symmetry. It's not because of supersymmetry. It's because my theory had symplectic invariance.
And that's a special property of Kerr Newman?
It's a special feature of my embedding. It's a special feature of my embedding. I mean, so Kerr Newman, because his Maxwell theory certainly has this, but then how did I embed it? Did I respect suitable phase symmetry? In fact, do I have things there? I do actually have there. So there's a little bit more to it. Indeed. So we have the symplectic invariance. It's not the same as duality. Maxwell field, yes, is duality invariant. It's not true duality invariant. It's standard phase. But the embedding is a little bit non-trivial here. From the point of view of the symplectic symmetry, this has an I index. This also has an I index. Very nice. That means that once you do a symplectic symmetry transformation, F is being acted on, this is being acted on, this one is not being acted on by symplectic symmetry. It's symplectically invariant from the n equal 2 point of view. So it's not one of the things that has complicated transformations that Gabriel was spelling out. From my point of view, it does not complicate heat. There's no complicated transformations at all. In fact, the way you should instead analyze this equation is that you should remember that n equal 2, you have yet another symmetry, you have an R symmetry. Under the R symmetry, this one here is actually neutral, but X is charged. So what I have to do is that I have to make this one negatively charged. So the electromagnetic duality symmetry, which is certainly part of my Einstein-Maxwell theory, the way it emerges here is because I have my U1 R symmetry in n equal 2 supersymmetry. So it was actually, in some other way, one can say that R symmetry that I should blame for the fact that my theory, in fact, has this sort of, this is where the standard Dirac duality symmetry came from. It did not come anything from the symplectic symmetry. That's good. That's why I don't need to do a lot of work. We already did work for the heat kernels. Surely don't want to do more work. So it doesn't always work out like that. But anyway, here we do not have to consider the symplectic symmetry and do the kind of careful analysis and such, going back and forth between different frames. We do not have to do that. So is that clear? Yeah?
If you look at the more general black holes with scalars per non, then you would not be able to say
I will not.
this is a
That's right. And that's
because
right.
of that relation there is specific to.
That's right. And we tried some of that. This is right. That's right. So we cannot, in those cases, we can in general not express things in terms of geometry alone. Basically, we will have new invariants, and new invariants are gradients of scalars. And they can be put together in duality invariant forms, and they can appear, and they do appear.
Yeah, so in line with Rob's question, so if the theory is not supersymmetric, we just modify A and C. Is that correct?
That's right. That's right. That's right. There would be different values for A and C. That's right. And a special case for that, for example, is what if you just threw away the fermions and had just your bosonic theory?
Well,
Make my boson couplings very special, but it's not supersymmetric. Fermions.
But I need to keep the order of symmetry, go to the supersymmetry.
Well, I would say not really, because I mean I do after all just in my Maxwell theory. I mean it depends on what. Well, I don't know. I think I took this principle from the beginning that I wanted a Maxwell theory that will have duality symmetry. It's not a priori clear when I then say, and please go embed it in some way into n equal 2 supergravity. I might not have known how you did it, but I'd say, well, somehow you must have had the duality symmetry come from somewhere. Whatever way you did it, right? It might not be the same way as me, but it came from somewhere. For me, it came from Larsen. So it came in a particularly pretty way. Yeah?
You could have started with, say, n equals 0, just start with some massless scalars coupled to U1 fields.
Yes, sir.
And right up, you could do exactly the same calculation right up until you get up to the heat quantum calculation.
That's right. And the reason I didn't do that is because that's what Sen already did.
Yeah.
So,
but then once you
disingenuous to write the same paper.
maybe try work on the sort of minimal conditions. Anyway.
So yes, one could do such things, and you know, some people have done such things, and so at this point we have some output from all our heat kernel computations on values of A and C, and those values are non-standard values because we have these non-minimal couplings. So what do we do then? Well, we go and take tables of our little A and C, but then we also remember that at some point what I'm going to have to do is that I'm going to have to do an integral. What I wanted was to find a correction to the entropy that has some kind of law, and that had a dimensionless function in front. So it's a function of dimensionless variables, but in principle, in my Kerr Newman kind of context, it's actually a function of two different dimensionless variables. It could be a rather complicated function. However, the A term was chosen very specially. This combination of Riemann and Ricci was chosen with a nice coefficient. The relative coefficient was such that you got exactly the Euler invariant. The Euler invariant is topologically invariant. And for that one, the integral is really easy. So this is why we chose this particularly linear combination. If we tried to integrate over the Riemann squared, it would have been complicated. If we integrate over the Ricci squared, it would have been complicated. When we do precisely this relative coefficient and choose it right, it's nice. It's 2. In particular, it's not just that it's a number, it's something that does not depend on these parameters. Right? It's a function that is the trivial function. But there's also the orthogonal linear combination, the one that was chosen as Weil squared. And if you do that integral, if you get a dimensionless function, and well, it could have been complicated, and it is complicated. I have in fact defined all the notation here, but this is even suitable for even a single slide only because I use things like the horizon location and temperature to make things a little bit smaller. There really is an inverse tangent. Things come to 5th power and 3rd power, and So in other words, in general, we could have got complicated functions, and in general, we do get complicated functions. So there, this is a complicated function. So now we should try to look at our results. So let me first present what are the contributions from the boson. So again, I have 4 different kind of multiplets: Hilberts, vectors, extragravitini, and my supergravity multiplet. For each of these, I compute A and C. And then I tabulate them. And these are my results. So for example, for the boson here, I would go and look and say, this number here, 2 divided by 60, that is the C value for my boson in the hypermultiplet. This one down here is then the A value for the boson in my hypermultiplet, and so on for the other kind of multiplets. In fact, the bosons that I just looked at here, the bosons in the hypermultiplet, they are minimally coupled. They did not have any extra F minus or any fun stuff. So therefore, these coefficients that sit out here, they should agree exactly with what I found in my textbook. And they do. We didn't really do a new computation. We literally copied, right? And it's the same thing with these ones here. It's a 31/9. You might even look familiar to aficionados in this game. It's what a vector field gets for the A value. And that's because the vector field that is the partner of a gravitino turns out to be a minimally coupled vector field. It doesn't have any extra funny couplings, so this coefficient here really is the standard coefficient. On the other hand, the vector multiplets, as I already had emphasized, they had non-standard couplings. So these coefficients here is somehow the coefficients for a complex scalar mixed with the field strength with a particular coupling. So there I wouldn't be able to say separately what came from the scalars, what came from the field strength. It's a package deal. This is where we got some extra contributions, and where these numbers here have been different from standard. Similarly, these ones here are different from the ones that would be quoted for gravity in the textbooks, because there were different couplings. And for fermions, the situation is reversed. It turns out that for fermions, there was a non-trivial coupling here that I showed it to you. They have a non-trivial Pauli coupling, but the fermions in the vector multiplet are trivial. So for fermions, we get trivial results for the opposite. So for each of these different 4 kind of multiplets, one kind of field, fermion or boson, is standard, minimally coupled, the other is not. So what are the results? These are from the bosons copied from the previous slide. These were from the fermions. And what you would notice is, that's pretty striking, is that this line here and that line here, they are exactly cancelled. So the fermions and the bosons, multiplet by multiplet, cancel. The C value cancels, and the A values, well, they will add to something. This is a huge simplification. Right? Before we look at the actual numbers, it's a huge simplification because remember the integral over the W squared was really complicated. But the coefficient in front of the W squared is 0. So I do not get any of these complications. I do think this is a genuine surprise. Because what people previously would have done is that they would have analyzed the situation of the BPS black hole. And in fact, they would have gone to the near horizon region. They would have done just ADS2 plus S2, which is a space-time where Weil squared itself is 0. So things would have simplified, but people might have said, oh, of course it simplifies. It's because it's conformally flat, this space-time. What I'm saying is that actually that too, if you're in a supersymmetric case, but you wouldn't have noticed then that the coefficient was also zero. Like it was sort of a double zero. It was zero for two reasons. In the BPS case, and it's for the second reason that things stay simple even when you go to the non-supersymmetric situation. When you go to these black holes that are not sure supersymmetry. But the theory does. Then I still get the simplifications. And now my space-time, of course, is absolutely not by that anymore. This is just a general black hole. It's certainly not by that. Complicated integral. The coefficient of the complications is zero. That's nice. So where are we at? So let me just summarize just, this is not the full summary, I do think I have a few more minutes, right?
About 8 more minutes.
Yeah, perfect. So this is where we're at now. The logarithmic corrections were computed. They depend on only the Euler invariant, so now you go and add up the numbers from the previous slides. And what you find is that the coefficient that we wanted, the log, the coefficient of the log, is universal. By universal, I mean it depends on the theory. I mean, it depends on how many vectors and hypers you have. It does not depend on your prepotential. It could have depended on your prepotential. It could have depended on the calorimetry. It did not. It could have depended on the parameters of the black hole. It did not. It's just a number. And in fact, that number is now a number we could say, oh, but since it does not depend on the black hole parameter, that number has to be the same as it was already in the supersymmetric case, because it doesn't depend on the parameters. So in particular, since I got out of my way creating a family that was such that I could go to a limit that was the supersymmetric limit, I should be unsurprised that these numbers are exactly the same as they were for the supersymmetric case. After all, it doesn't depend on the black hole parameters, right? So the way you can think about it is that the log is incredibly robust. Sure, we knew that we could compute it in the low energy theory, and that gives us some kind of window into the UV theory. But what perhaps was a lot less obvious is that that log that you would think about as having a certain microscopic origin in the microscopic theory in the BPS case, you can deform that all the way off. And it seems to me plausible that one might be able to understand that, even for the non-supersymmetric black holes, that somehow the microscopic theory has to keep giving the same moment. It has to have an origin that should be traceable, even in this non-supersymmetric situation. There's a little caveat on fermion zero modes, but examples, but I will not go there. Experts can ask, and there are good answers. But of course, I should also at some point come back to, well, fine, this was by explicit computation. You got this C equals 0 by just computing and adding. This is what it gave. Why? The background is not supersymmetric, so the fluctuations around the background are not themselves in supermultiplets. But we saw that they kind of fit into supermultiplets. It looked like they were supersymmetric. Well, if you think about this in background field formalism, what you can do is that you can realize the symmetry of your theory explicitly. That's what background field formalism does, is that the dependence on the background fields has to respect all the symmetries, and in this case I'm in a supersymmetric situation. So what I should expect is that if I think about this whole expanding around a background as computing quantum corrections in background field formalism, I should argue that my terms that I get, in fact, should be the supersymmetric terms. So this is where Shahin's question comes in. These funny terms with R and F squared, whatever, shouldn't they somehow be related by supersymmetry? They should. They should. So schematic, the way you think about it is that I shouldn't really have written just Biot squared with a coefficient in front, Euler with a coefficient in front. I did that because I had all these field strengths, and I was very happy that the field strengths could be traded for geometry, and that I could write everything in terms of only the standard A's and C's. But of course, that way I'm not online. But of course, I could also decide that I would write things in a different way, where I would say that I really should respect supersymmetry. I should write a Biot squared plus my superpartners, which is various kind of f to the fourth terms, whatever, with some coefficient in front, and I should write these ones here with some coefficient in front. In this way, I would get a new perspective. The way I would think about it actually is that these A and C coefficients I would now think about as being kind of like the beta functions for these extra operators. That these extra operators are dimension 4 operators, so they have nice logs that, as usual, and these logs, they have beta functions. These are beta functions for some operator, and one can say that's what I have a computer, I give the beta function for certain operators, that's a very standard thing. And when I think about it from that perspective, of course I should write things in nice supersymmetric form. Now, details of the actual action of doing this, of making this explicit, is unfortunately kind of hard. You know, you need standard sort of superconformal realization of off-shell supersymmetry, there are a lot of auxiliary fields, there are details involve a lot of hard work by very brave people, which is not me. But this has been done. And the superpartners to the biospheric were identified a long time ago. In fact, again, they appeared at least behind Gabriel's slides. I don't think they were literally written. This is where he said that, yeah, well, kind of, was it cheating? Anyway, there were some words involved here. But they have been identified a long time ago, what these things were. However, and the structure of the on-shell structure for these widespread things has also been known for a long time. The structure is very interesting. If I take my Weyl square and I add these SUSY partners, basically various kind of field strengths, if I simplify, I can simplify this and it gives none other than the Euler term. So the supersymmetrized Weyl, in fact, is Euler. And that people have noticed before. The cartoon is that there's an elaborate cancellation between these gravitational terms, Weyl squared here, that actually have some Ritchie with a particular coefficient. Then these things here has various R, F squares and F squared. If you use the Einstein equation, you get some new geometry terms. Those geometry terms go together with the Ritchie in here and exactly conspire to give the Euler. Not obvious that that should happen, but it's true. As I say, that has been known for a while. But what about the other guys? What about the Euler? Because there too, I have to supersymmetrize. This was done only in the last couple of years. Duity and a couple of collaborators. We go and look at those terms in those papers. If you go and actually write out this cartoon, the Euler plus the superpartners, what you'll find is that in this case, the superpartners, when you go on shell, vanish by themselves. So that the supersymmetrized Euler also reduces to the Euler. So therefore, all the matter terms can be eliminated just in favor of geometry alone, and both the linearly independent n equal 2 invariants, in fact, reduce to just the Euler invariant. That's the explanation for why is it that you couldn't have gotten a coefficient in front of the Weyl square. It simply wouldn't be allowed by n equal 2 supersymmetry. Both the invariants reduce to just this one. So should I do this? So this is just almost the previous summary, but also really just the explanation of these high derivative terms. We've investigated various aspects of it, but I think we're at the saturation point. So thanks for your attention. More questions? Yeah.
You really only considered single black.
Yes.
I don't know if you can run the same machine for example, ABS and
That's right. So that's a very interesting problem. So gauge supergravity. Why don't you try to embed your black holes into gauge supergravity? Well, I could try, but I would have to do hard work. And this would be interesting work, I think. Of course, I would have to start with a solution that somehow was my standardized solution. Perhaps I would say that would be my ADS Weissman-Morström. And then I would try to embed that into this theory. And could that be done? Most likely. I haven't done it. But can one find a nice embedding? After that, go find quadratic fluctuations. I suspect it will be harder. But is it in principle straightforward? Yeah. I mean, algorithmically, you know, what could fail is maybe my embedding will not generalize. In that case, maybe there's some reason it wouldn't generalize. I don't know. Right? I mean, it's not guaranteed that there's a nice way to do this. And the difference between a nice way and a not nice way is that once it's a not nice way, then everything becomes also totally non-universal. That's as in, what's the view potential? Exactly which n equal 2 theory. Or, you know, then, I mean, sure, then I'll take the STU model, then if I absolutely must pick, then, but, you know, so that these such things, such additional complications could happen, that you would have to write one paper for each n equal 2 model, and that's a lot. Work for many practitioners. Yeah.
That's related. C equals 0, it's still all in that case. It's the same argument. So you only have to compute A.
I don't think so. So what I mean, so these supersymmetry invariants that I had here were supersymmetry invariants in non-gauge supergravity. So have they even been constructed in the gauge supergravity? Maybe, but I'm not sure. I mean, but anyway, I have not done the work, so I'm not claiming anything.
You can repeat your arguments why supersymmetry implies C equals 0 and why that. Yeah. No.
That I knew a priori that my effective action, this is my Wilsonian effective action, should preserve supersymmetry because my theory has supersymmetry even if my solution does not have. That's how background sort of formalism works. The background thing has to preserve supersymmetry. So I knew that in cartoon, this is what I have to get. Some coefficient times the supersymmetrized by some other coefficient times the supersymmetrized Euler. Now I need to go and figure out, what does this cartoon here mean? Well, what it means is some concrete terms, which I didn't write down, but those concrete terms are such that this thing here becomes some terms that actually basically gives the Einstein equation squared, plus a few other terms that combine with this so that this one is transformed into Euler. So that means that this thing here will actually, this one here will contribute, this coefficient will contribute, despite what it might appear that it will contribute to the C anomaly, it actually won't. This one will contribute to the A anomaly, because this one here is actually Euler. Then this one here, it turns out also to be Euler. So therefore this one and that one will contribute to the A anomaly. Neither of them contribute to the C anomaly. Well, we're done. Other questions? Yeah?
Can you do this for space dimensions?
For what?
For other dimensions other than 4.
Well, so the entire log game, for one thing, is not so interesting. It's only interesting in even dimensions, because I mean, it's a little bit interesting also, for example, in 5. But there, most of it comes back from some ensemble business and stuff like that. It didn't really come from intrinsic quantum effects. So anyway, so one can provoke, one can try to find some things, but so yes, next up 6. But I don't know even of that many interesting black holes in 6 dimensions. And then after that, I have to go and digest the papers on invariance in 6 dimensions, and those papers are less well digested than these ones. And these ones were still a little bit of effort to actually dig them out. This cartoon here is being too nice. it's actually not all that pleasant.
Well, in 6 dimensions you don't have supersymmetric black holes.
Yeah.
So
No, but I don't care if the black holes are going to.
no, but you care that it's continuously connected to the VTS solution.
Yeah, not necessarily. Maybe. Yeah. But look,
Embedding is
a lot of pieces are missing. That's right. Yeah.
When you said Kerr Newman, I guess you meant an over-rotating Kerr Newman in the sense that you cannot. Did you mean over-rotating or
Under-rotating?
Can you switch off rotation?
Yes.
You can switch off rotation.
Yes.
And it's the under-rotating.
Yes.
I see. So you're
That's
not.
right. That's right. It's specifically
You cannot
not
go
the
to Kerr. You cannot go to Kerr to Kerr.
No, sure.
Sure.
Yeah.
So you can switch off the charges.
Yes. That's right. That was exactly the point of trying to say also, remember the attractor mechanism. That there you'd say, look, how could you possibly get an attractor mechanism for a neutral black hole? Well, I have one, but my attractor mechanism just happens to, instead of giving nothing, it just gives something trivial. So at least it's correct. But basically saying that once I have no charges, my scalars feel no forces. So therefore I can take them to be any value they want. And therefore my attractor mechanism is you specify the scalars, and I will tell you which of the field strengths should you identify with your Einstein-Maxwell. Well, the Einstein-Maxwell, you're telling me no longer is turned on. And I would say, so pick any one of them, because you shouldn't turn them on. Right? So I turn all of my NP+1 field strengths off. That was a very simple embedding, right? That I didn't turn on the field strings up.
So sorry, so you cannot switch off rotation.
I can switch off rotation. I can switch off rotation.
But you were just saying that you could also switch off charges.
I can switch off charges.
So-
I can switch off charges. I'm saying that in that case, a lot of the work actually became trivial. If it didn't become incorrect, it still applies. It's just that all my non-minimal couplings now are no longer there. So therefore,
So this applies to both under-rotating and
yes,
over-rotating levels.
that's right. That's right. That's right. And as I say, that once it's pure gravity, if you did pure gravity, Kerr Newman is a special case, but basically it's Kerr. I'd say everything goes on, but it's not as much interesting anymore. Because in that case, for example, also it's Ritchie flat. You know, you ask a question, is Ritchie flat? Once it's Ritchie flat, I knew that the Weil squared would become equal to the Euler, because all I have is the Riemann squared. So therefore, you know, the results are correct, but they are sort of less interesting. So that's why this is not the part that's being emphasized. All right.
All right, so if there's no further questions, let's